Hello, everyone. My name is Hong Pan, and we are from the University of Illinois at Chicago. Today, please allow me to introduce our paper, Modification Avoiding Variant of Power Iteration with Applications. Here is today's outline. First, I will introduce what is power iteration. Then, I will go over modification avoiding vector products and modification avoiding power iteration. And finally, I will report our experimental results and make a conclusion. The regular power iteration can be computed in this way. Given a diagonalizable matrix A, for example, a covariance matrix, we randomly initialize a vector B, and we compute A times B and normalize it with the L2 norm of the product. With sufficient iterations, B will converge to the dominant eigenvector of A. Now let's discuss our two operations. In our paper, we propose two operations based on sign and minimum. We call them min1 and min2. The min1 can be computed in this way. That is, sign of xy times with the minimum of the absolute value. So this one is modification free because the only modification is from the sign operation, but it can be also achieved using beta operations. So we don't really need the modification here. And here are two examples. Our min1 operation on 3 and -1 is -1. This is because sign of 3 times -1 is -1, and the mean of the two absolute values is 1. So -1 times 1 is -1. And the mean operation on 2 and 3 is 2. Here is the vector form. So we're just revising the vector product by changing the modification in the vector product to our min1 operation. Here is the kernel equation. The kernel is a multi-step kernel because if we build the Gram matrix using this kernel, the matrix is positive semi-definite. The operation also holds L1 norm property because if we take our min1 operation on a vector transpose with the vector itself, it will return you L1 norm of the vector. Now let's talk about the min2 operation. We reverse the sign operation here. Instead of taking the sign of xy, we compare the sign of x and sign of y. If they are equal, we return the mean absolute value. If they are not equal, we return the 0. And here's a vector form. So this one can only return the non-negative results. And here's the kernel form, and it also holds the property, L1 norm property. We can also extend it to the matrix form by replacing the multiplication in the matrix product, and we can build our covariance matrix in this form, so it will be very close to the covariance. Now let's talk about the MAPI, modification avoiding power iteration. The regular power iteration can be computed in this way, as we mentioned before. So we just replace the modification with our min1 or min2 operation. Instead of normalizing it with L2 norm, we normalize it with L1 norm because our operation holds the L1 norm property. But we can normalize it with the L2 norm after all iterations because the eigenvector usually have the L2 norm equal to 1. This one is very energy efficient because we only perform one division in each iteration. And we only have sign and minimum calculations. So this calculation is much cheaper than the modification. Now let's talk about the experiments. So the first experiment is the image construction. It follows the recursive L1 PCA paper in our section 68. For example, here in this Pikachu, we want to reconstruct the image A, but we don't have it. What we have is that 10 occluded images like B. So we have different noise patches in the 10 images. And we want to reconstruct the original image from this occluded images. So we will get the result of C, which is the result from the recursive I1 PCA, and D, which is the result from the regular power iteration, and E, which is the result from our mean power iteration, F, the result from our mean power iteration. So how do we do that? We take the we compute the covariance on this 10 matrix on these 10 samples, and then we compute the two eigenvectors corresponding to the two largest eigenvalues. So we got this vector space, and we do the projection on with the arbitrary images on the vector space. So we can get the reconstructed imaging in this way. So I have to say that which one works better, which one works worse. It will depend on the image itself, but globally, in average, our mean to power iteration it returns the highest peak signal to noise ratio. So this one, the larger the better, because this is the signal to noise ratio. And also the C, E, F, these three methods are all hold I1 norm, and the D holds the L2 norm. So that's why these three are significantly better than the D. Now let's talk about our second experiment. So in this experiment, we will do the power iteration on a synthetic data set. The data set is in 10 to the 6 by 10, which means that we have 10 to the 6 samples, and each sample has 10 entries. The covariance matrix has an eigengap of 0.1. How do we do this in the experiment? We first compute the eigenvector using the eigendecomposition. I mean, using the EIG function in MATLAB. So that is U1. And then we compare the result of the power iteration. WT, T means that at the T3 iteration. For example, W3 is the result at the third iteration. So we compute we plot the T versus this one. So this one, I mean, what's in square is that the angle, it shows the angle between WT and the U1. So if this one, if the two vectors are in some orientation, the entire equation will be 0. So the regular power iteration can converge to the exact same place as the dominant eigenvector, but our method, because the calculation is different, so we don't have the exact same results. What is interesting is that after 100 iterations, if we get these two matrices, one is from the regular power iteration, another one is the MAPI. Here we only use the mean one operation because the mean two can only return the positive entries. When we saw these results, we found that the second one is the largest in both ways, and the ninth one is smallest in both ways. So I mean, their ranks are the same. And you can see that our methods converge much faster than the regular power iteration. So we think that maybe our method can be used in the PageRank algorithm. The detail of the PageRank algorithm will be stated in the experiment 3. So another thing is that although they did not converge to the same place, but you can see that our methods converge at 20 epochs, 20 iterations, and the regular power iteration converges at 60 iterations. So if we can also do it this way. So use our MAPI first, will run until it converges, then switch to the regular power iteration. So it will it will also faster than the regular power iteration. The third experiment is the PageRank algorithm. So this one is developed by Google for the search engine. That means that if you search a keyword, what will be shown in the first page will be determined by this algorithm. So in detail, it will create the PageRank matrix on the network graph, based on the network graph, and then run the power iteration on the matrix. So for example, in this toy example, there are 4 nodes. So the matrix will be 4 by 4, and we run power iteration, and the modification avoiding power iteration. So you can see that our conversion is much faster than the regular power iteration, and the ranks are the same. So I mean, which is the largest, which is the second largest, that one is the same. We also tried the Nutella dataset. Then because the previous dataset only have 4 nodes, this one has thousands of nodes. And you can see that our method also works faster, converges faster than the regular power iteration. So if we choose the top 10 of the results, we can see that there are 7 common in from Nutella 08, which has more than 6,000 nodes, and 8 from the Nutella 09. Of course, the order may be a little different, but it doesn't matter, because if we use this one in the PageRank algorithm, what will be displayed on the first page will be very close. Maybe the order is a little different, but that is not important. So in this way, our method can accelerate the PageRank algorithm efficiently. And if you are using our method, so your searching experiments will be better, because you don't need to wait. You can wait for a shorter time. Okay, so now let's make a conclusion. So today we introduced the 2 merge-type kernels, min1 and min2, and we proposed the 2 modification avoiding power iterations based on these 2 operations. In our image reconstruction experiments, our min2 power iteration returns the highest average peak signal to noise ratio, and it overweights the recursive I1 PCA and the regular power iteration. Our peak converges faster than the regular power iteration in the synthetic dataset experiment and the PageRank experiment. So that's all. Thank you for your listening. And here's my email. If you have any question, please let me know. Thank you.